Hello everyone. Today we will be diving into a fundamental concept in computer science, which is the linked list as a data structure. So, linked lists are essential for understanding dynamic data storage as they allow for efficient memory utilization and flexible data manipulation. So, unlike arrays, which require contiguous memory allocation, linked lists offer the ability to easily insert and delete elements without the need to shift data. So then let's get started. Now let's move on to understanding the list abstract data type or ADT. At its core, a list is simply a collection of elements where each element holds data. This structure allows us to perform operations such as adding, removing, or accessing elements within the list. The elements of a list are often thought of as individual data items, and they can be manipulated using various list operations. These operations are what make lists such a versatile data structure, allowing us to modify, traverse, and manage the data in efficient ways. We'll be covering some of those operations in detail shortly. So, this fundamental understanding of lists will help us see how more complex data structure, such as linked list, build on these core principles. So basically ADT, which is abstract data type, is a theoretical concept used in computer science to describe a data structure purely in terms of its behavior without specifying how it is implemented. So an ADT defines a set of operations that can be performed on a data structure and the type of data it can hold, but it does not detail how those operations are carried out or how the data is stored internally. So here, like, if in simpler terms, you can think of an ADT as a blueprint for how a data structure should behave. For example, a list ADT might specify that you can add, remove, or access elements in the list, but it won't specify whether it's implemented as a linked list, an array, or something else. So these are the operations we can do, like insert a new item into the list, iterator for retrieving, like by copy instead of removal each item from the list one at a time. At any particular moment when an item is retrieved, that item becomes the current position in the list. Find to determine whether or not a certain item exists in a list or not. If the item exists, it becomes the current position. Retrieve to retrieve by copying instead of removal a certain item, that item becomes the current position. Next we have replace to replace the item at the current position with another item. The current position remains unchanged. Then remove to remove an item from a list. There is no current position after a removal. An operation to determine whether or not the list is empty. The current position is unchanged. An operation to empty out the list. The current position is lost. So these are the operations we can do. Now we'll learn more about these things. Okay, so let's see the retrieving elements. So we'll see how we can how elements are retrieved from a list. Typically, the primary reason for retrieving an element is that it holds some information that the client or the user of the list needs. However, for a client to request a specific element, they need to know something about it beforehand. This leads us to the concept of the key, The key is some unique piece of information that identifies the element the client is looking for. Without knowledge of this key, the list object would not know that what to search for. So, um, so the client needs to provide the key, which allows the list to locate the desired element and return it. So we'll also learn how these keys work in different types of data structure in the coming slides. But the important takeaway here is that retrieving an element depends on knowing something unique about it, such as its key. So continuing from the previous slide, let's see what is key. So a key is a value that uniquely identifies an object in a list or any other data structure, just like how a social security number uniquely identifies a person. So a key in a data structure helps us to locate a specific object. For example, in a collection of books, the ISBN acts as the key because it's a unique identifier for each book. Then, in a list of parts for an inventory system, the part number would be the key, distinguishing one part from another. So, in a list entity, the elements are typically objects, and the key is simply one data member of that object. By knowing the key, we can efficiently retrieve or manage that specific element in the list. Okay, here is an example. So, a customer of an insurance company has a problem with the amount paid by the insurance company for an operation. The customer calls the insurance company. The insurance company asks the customer for the claim number, the key. So here is the claim number is the key here. So the customer provides the claim number. Then the insurance company representative types the claim number key into the computer. Then the claim number is typed into a program which is using one or more data structures. The retrieve function of a data structure is called passing in the claim number. Then the retrieve function searches the data structure for the object that has the key. The retrieve function finds the object and returns the object. All the data in the object is now provided to the main program. The main program shows all the data on the screen. The insurance company representative looks at the data. The insurance company representative can now see what the customer is complaining about. This is how the whole operation or the whole process is. When you have a key, that key is the unique identifier. By the help of this key, you can search or retrieve any data. Now let's talk about how lists are implemented in C++. Lists can be implemented in two main ways, using arrays or linked list. Both methods have their pros and cons, but today we are going to focus on linked list as we are learning linked list as data structure. So we'll now focus on linked list and we'll see all the examples and all these features which is related to linked list, not array. Now there are two major advantages of using linked list. First is memory efficiency. Linked list conserve memory, particularly for large objects. This is because unlike arrays, linked lists do not require a continuous block of memory. Then second is efficient removal of elements. Linked lists allow us to easily remove an element from the middle of the list without needing to shift other elements as we would do in array. So it is not like array. From this point forward, we'll focus on the linked list implementation instead of constantly referring to the linked list implementation of a list. We'll simply say linked list for simplicity. Okay, now we'll see. Um, Now let's look at how we can implement the retrieve function in a linked list. This function will allow us to retrieve an object using its key. So there are two main approaches to do this. Approach 1 is we pass the key into the retrieve function as a parameter. Along with that, we also pass an object as a reference parameter. The reference parameter allows us to modify the object directly and return the result of our search in the object passed by reference. Then on second approach, we can in this method we pass the object itself by reference with its key already set to the value we are searching for. The retrieve function will search for this key in the linked list, and once the object with the matching key is found, it will be assigned to the object passed in by reference. Both approaches allow us to efficiently search for and retrieve an object using its key, but they differ in how we handle the object and key parameters. The choice between these approaches often comes down to how we want to handle memory and object management in our application. So here, we'll see there are some advantages or benefits of approach 2 when implementing the retrieve function. Let's say in this approach, where the client only needs to declare an object which will hold the data retrieved from the linked list. This is more efficient because the client doesn't need to declare a separate key. The key is already embedded within the object itself. If we were to use approach A, we would need to declare two data types, one for the object type and another for the key type. This can add complexity to the implementation. For instance, if the object was a data type 1 and the key was a data type 2, we would need to handle both data types separately. Additionally, approach 2 simplifies operations like find and remove, as the same object-based mechanisms can be used for those functions as well. By using this approach, we streamline the code and make the client's job easier by reducing the need for managing separate keys. So now let's walk through the retrieval process step by step. First, an object is created in the main program. This object will eventually hold the data retrieval from the linked list. Next, the representative or the person using the system asks the computer or the customer for the key. This key is what will help us identify the specific item we are looking for in the list. Then the representative types in the key, which is then associated with the object. The object's data member is set to this key value. At this stage, none of the other data members in the object are set. So only the key is needed for the search. Finally, the object, let's call object 1, is passed into the retrieve function by reference. The retrieve function will then use the keys stored in the object to search the linked list and return the corresponding data. So this process demonstrates how the retrieval of the data works in a particular system, ensuring that we can access the correct object in the linked list efficiently. So we'll see, we'll continue it here. So the struct for the object, which we were calling object 1, has an overloaded operator. This operator is used by the retrieve function to compare the key we provided with the key of the object in the linked list. Now, for example, we could use a condition like if object 1 equal to pointer info to check if the keys match. If they match, it means we have found the object. Once the object is found, the other data associated with the object is placed into object 1. So, object 1 equal to pointer info will assign the full information from the list node to the object passed by reference. Then finally, the retrieve function will return true to indicate that the object was found, and object 1 is returned by reference, meaning the calling program now has access to the full object information. So this is how the whole process shows how we can use operator overloading and references to efficiently retrieve and return objects from a linked list. Okay, so we will now learn about iterator. So an iterator is a tool that allows us to traverse through the elements of a list one by one. Now the first function returns the first element in the linked list, which acts as the starting point for our iteration. The getNext function returns the next element in the list after the first function call or after the previous getNext call. This is how we progress through the list, element by element. The iterator implemented by maintaining a current pointer in the private section of the class, which keeps track of where we are in the list. Each time the getNext function is called, this pointer is advanced to the next element. If the client tries to call getNext when there are no more elements in the list, the function will return false, indicating that we have reached the end of the list. Otherwise, it continues to return true as we traverse through the list. Next, we will explore two key operations often used together, the find and replace function. The find function searches the linked list for an element with a given key. It returns true only if an element with the specified key is found. It's important to note that the element itself is not returned, just the confirmation that if it exists. Then the replace function is used to replace the element at the current position in the list with a new element that is passed into the function. This is useful when you want to update the data of an existing element without changing the structure of the list. Often these two functions are used together. For example, you might first find an element and then replace it with a new value once you have confirmed its existence. Now let's discuss the implementation of a linked list. A general linked list is more complex than specialized type like a linked list queue or linked list stack. This is because in a general linked list, the client must be able to access, change, or remove any element in the linked list at any time. When implementing a linked list, it's crucial to make it flexible enough to handle objects that are key oriented, objects that are identified by a unique key. However, we also want the implementation to be general enough to manage other types of objects that may not have keys, such as simple data types like string. By keeping the elementation general, we ensure that our linked list can be used in a variety of applications, not just those that depend on key value pairs. Now, if you see here, in some data structures like hash tables and graph, Arrays of linked lists are used, and many of those linked lists could potentially be empty. While a header node can simplify the code by acting as a placeholder or starting point, it does come with a trade-off. Specifically, it uses more memory, which is especially unnecessary for empty linked list. And it's important to note that in our approach, we won't be using a header node. So, therefore, although a header node can offer coding simplicity, it isn't always the most memory efficient approach. For our implementation, we'll avoid it to save space, particularly when the linked list could be empty. Okay, so now let's take a look at the LinkedList.h, which is a header file which defines the structure and the implementation of our linked list. We begin with the declaration of a template which allows us to define the linked list for any data type. Inside the template, we define a node structure which contains two key elements, info and next. Info, which holds the actual data of the node, which will be of the data type. Then next, which is a pointer to the next node in the list, allowing us to chain the nodes together. After the node structure, we define the linked list class itself also as a template class. The class will have two constructors: the default constructor, which initializes an empty list, a copy constructor, which allows us to create a new linked list as a copy of an existing list by passing it as a parameter. Okay, so let's go to the next slide. Here we are, we'll see some of the key methods defined in our linked list header class. So we have destructor, linked list which is responsible for cleaning up and deallocating any memory used by the linked list when it's no longer needed. The assignment operator, which allows us to assign one linked list to another by copying its elements. The insert method allows us to add new elements to the list. The first and get next methods are used to traverse the list. First sets the current pointer to the first element, while get next moves it to the next element in sequence. The find and retrieve methods search the list, and find checks if an element exists, while retrieve fetches the actual element. Then 6, we have the replace method allows us to update an element at the current position with a new value. The remove method deletes an element from the list. The isEmpty method checks if the list is empty. The makeEmpty method clears the entire list by removing all elements. Now here we have the private section of our linked list class, where we define the key internal member variables and a helper function. We have start, which is a pointer to the first node in the linked list. It helps keep track of where our list begins. Then current, this pointer is used to keep track of the current position in the linked list, which is useful for traversal and other operations. Then we have deep copy. This is a helper function that allows us to make a deep copy of a linked list. A deep copy ensures that all nodes and their data are copied from one list to another, rather than just copying pointers, which could lead to data corruption if the original list is modified. Finally, we include the LinkedList.cpp file where the actual implementation of these methods resides. The CPP file will contain the logic for all the functions we have defined in the header file. Here we'll see the constructor or the copy constructor. Here the default constructor is responsible for initializing an empty linked list. As you can see, both the start and current pointers are set to null, indicating that the list is initially empty and there are no elements to traverse. Then the copy constructor allows us to create a new linked list that is a copy of an existing linked list. When a linked list object is passed by reference into the constructor, the deep copy function is called. This ensures that all the nodes and data from the original lists are copied over to the new list without simply replicating the pointers. This is important because it prevents issues such as data corruption or dangling pointers when dealing with multiple instances of linked list. So by implementing these two constructors, we ensure that our linked list can be created from scratch or duplicated from another existing list. Now we have destructor. The destructor is automatically called when an instance of the linked list is destroyed or goes out of scope. In our implementation, the destructor calls the makeEmpty function. This ensures that all the nodes in the linked list are properly deleted, freeing up the memory that was allocated to them. By invoking makeEmpty, the destructor guarantees that there are no memory leaks, as it ensures that if every dynamically allocated node is removed from the list and the memory is returned to the system. The use of destructor is crucial because it's very important for memory management in a class that deals with dynamic memory allocation, such as a linked list. Okay, now we'll have overload assignment operator. The assignment operator is responsible for handling cases where one linked list is assigned to another. Here's how it works step by step. First, we check if the object being assigned this is the same as the object on the right hand side, our list. If they are same, we simply return start this to avoid unnecessary operation. Then if the two objects are different, we first call makeEmpty to clear the current list. This ensures that any existing data in the left hand side list is removed before copying the new data. We then use deep copy to copy the contents or our list, the right hand side list, into the current list. Finally, the overloaded operator returns start this, allowing for chain assignment if needed. This operator is crucial when we need to assign one linked list to another while ensuring that memory is managed correctly and no data is lost or leaked. Okay, now let's look at the insert function. First, we will set current to null to ensure that we start fresh with no current node selected. We then create a new node by dynamically allocating memory for it. This new node will hold the element we want to insert into the list. the info um, the info field of the new node is set to the value of the element we are inserting. Next, we update the next pointer of the new node to point the current start of the list. This means that the new node will become the first node in the list, and it will point to the what was previously the first node. Finally, we update the start pointer to point to the new node, making it the new head of the list. Inserting an element at the beginning of the list like this is a very efficient operation. It has a constant time complexity, um, and meaning it takes the same amount of time to insert the node regardless of the size of the list. Next, we'll see first function. The first function first check if the start pointer is null. If start is null, it means the list is empty. So the function returns false to indicate that there are no elements to access. If the list is not empty, we set current to point to start, meaning that we are now positioned at the first element in the list. Then the info or data of the first node is then assigned to the parameter list ei, which allows the calling function to access the value of the first element. Then finally, the function returns true to indicate that the previous that the operation was successful and the first element has been retrieved. This function is essential for initializing any traversal or accessing the first node in the linked list. Then we'll now move to getNext. Now, getNext allows us to traverse the linked list and retrieve the next element after the current one. First, we check if the current is null. If it is, it means we are not currently pointing to any element, so there is no next element to retrieve. In this case, the function returns false. If current is not null, we then check if current is pointing to next, which is null. This check determines whether the current node is the last node in the list. If it is, we set current to null and return false to indicate that there are no more elements left in the list. Then here, if there is a next element in the list, we move current to point to the next node by setting current equal to current pointer next. This advances us to the next element in the linked list. We then assign the info or data of the new current node to list ei, allowing the calling function to access the value of the next element. Finally, the function returns true to indicate that the operation was successful and the next element has been retrieved. By combining the logic from both parts of this function, we can efficiently traverse the entire linked list, retrieving elements one by one until we reach the end of the list. Now let's see how the find function works. This function searches the list for a specific element and returns whether or not it was found. We start by declaring a local variable item of type data type to store the elements as we traverse through the list. The function first calls the first function to move to the beginning of the list. If the list is empty or the first element cannot be retrieved, it returns false. Then we use a do-while loop to iterate through the list. Inside the loop, we compare the current item to the target element using the overloaded operator. This operator must be overloaded for struct objects to allow comparison of two data objects. If the current item is equal to the target element, the function returns true, indicating that the element has been found. If the element is not found, the loop continues calling getNext to move through the list. If the entire list is traversed without finding the element, the function returns false. This function ensures that we can search through the list efficiently, checking each element until we find, match, or reach the end. This explanation walks through each step of the find function. We'll see next we have so here we have if you just look at that, unlike the insert function which operates in theta 1 time, the find function does not have constant time complexity. The find function has a linear time complexity, meaning its performance depends on the size of the list. So now we'll discuss the retrieve function. The function first calls the find function, passing in the element to search for. If the element is not found in the list, the find function returns false, and the retrieve function immediately returns false as well, indicating that the element could not be retrieved. If the element is found, the current pointer will already be set to the node containing the desired element. We then assign the info from the current node to the element parameter, effectively returning the data to the calling function. Finally, the retrieve function returns true, indicating that the element was successfully found and retrieved. Next, we have replace function. The function first checks if the current is null. If current is null, it means we are not currently pointing to any node in the list, and therefore there is nothing to replace. In this case, the function returns false to indicate failure. If current is not null, we proceed to update the info field of the current node with the new element value and replacing the existing data in that node. Finally, the function returns true, indicating that the replacement was successful. Next, we have remove. The function begins by setting current to null, ensuring that we are not currently pointing to any node in the list. Next, it checks if the start pointer is null. If start is null, it means the list is empty and there is nothing to remove. In this case, the function returns false, indicating that the operation could not be completed because the list is empty. Now we create a pointer ptr and set it to the start of the list. The function then checks if the info field of the node pointed to by ptr matches the element we want to remove. If the first node is the one to be removed, we assign its info to the element parameter to return the data. We then move the start pointer to the next node in the list to update the head of the list. Finally, we delete the node pointed to by PDR and return true, indicating that the node was successfully removed. Next we have while we enter a while loop that iterates as long as the next node after pointer is not null. This ensures that we don't go beyond the end of the list. Inside the loop, we check if the next node's info matches the element we want to remove. If a match is found, we create a temporary pointer to store the next node. We assign the info of temp ptr to the element parameter so the data can be returned. Then we update the next pointer of ptr to skip over the node being removed, effectively removing it from the list using ptr pointer next equal to temp ptr pointer next. The line on 121. We then delete the node pointed to by temp ptr and return true. If no match is found, we move ptr to the next node and continue searching. Now we'll see isEmpty function, which checks whether the linked list is empty or not. This function simply checks if the start pointer is null. If start is null, it means there are no nodes in the list and the list is considered empty. The function returns true if the list is empty and false otherwise. This is a very straightforward function. We'll see makeEmpty function, which is responsible for deleting all the nodes in the linked list and effectively clearing the list. So makeEmpty, the name makes sense now. If you see, we are trying to make the list empty. The function enters a while loop that runs as long as the start pointer is not null, meaning the list is not yet empty. Inside the loop, we set current to the start node, which is the node we will delete. We then move the start pointer to the next node, start equal to start pointer next, so that we can continue with the remaining nodes after deleting the current one. The current node is then deleted using the delete keyword, which deallocates the memory for that node. This process repeats for each node in the list until the start pointer is null, indicating that all the nodes have been deleted. Finally, after exiting the loop, the current pointer is set to null to ensure that the list is fully empty. Okay, so now let's talk about a sorted linked list. In a sorted linked list, the elements are inserted in a specific order, typically based on their key values. As you can see in the diagram, the nodes are ordered from lowest to highest, starting with 3 and moving so 4, 5, 7, 9. Each node points to the next node in the sequence, maintaining the sorted order. This is an example of a linked list that ensures that new elements are inserted in such a way that the list remains sorted at all times. Sorted linked lists are often useful in applications where it is important to maintain an ordered collection of elements, such as in priority queues or ordered data storage. The structure of the list allows for efficient insertion of new elements while maintaining the sorted order, although the complexity of insertion can vary depending on where the new element fits. So we'll see here the insertion complexity in a sorted linked list. Now, in a unsorted list, we can insert new elements in constant time theta 1, but so we can simply place the new element at the beginning. However, in a sorted linked list, the insertion complexity increases to theta n on average, because we need to find the correct position to insert the element in order to maintain the sorted order. Now, we can find and retrieve operations in the sorted linked list. Searching in a sorted linked list can be faster compared to an unsorted one, especially when the element is not in the list. For example, if you are looking for the number 6 in the current list, you can search 3, 4, 5, 7, 9. Now once you reach 7, you can immediately determine that 6 is not in the list because the list is sorted. This reduces the number of comparisons needed, although the overall complexity remains theta n on average. And then you can retrieve as you did for find. So it is sometimes it's easier compared to the unsorted linked list. Okay, now here is a example of a circular linked list. Now in a circular linked list, the last node points back to the first node, creating a continuous loop. This structure differs from the standard linked list where the last node points to null. The key advantage of a circular linked list is that you can traverse the entire list starting from any node, as there is no defined beginning or end. This type of list is useful in scenarios where it is beneficial to loop through the list continuously, such as in round-robin scheduling or in certain buffer implementations. In this diagram, we see that the current pointer is pointing to one of the nodes, and by continuously following the links, we would eventually circle back to the current node. This continuous traversal property is what makes the circle linked list unique. Now, here is an example of a doubly linked list. It is a variation of the linked list that provides additional flexibility. In a doubly linked list, each node contains two pointers. One pointer next points to the here if you look at this example, one pointer next points to the next node in the sequence. Another pointer back points to the previous node. This allows traversal of the list in both forward and backward directions, which can be very useful in certain applications like navigating a browser's history or implementing undo-redo functionality. If you see in the diagram, each node is connected to both the previous and next node. So the structure is more complex than a singly linked list, but it allows greater flexibility in accessing nodes from either direction. In this example, the DL node struct includes data type field for storing the data, a next pointer to the following node, the back pointer to the previous node. So here, now that we understand how a doubly linked list work, let's discuss removing a node from the list. Now here, if you see, removing a node involves adjusting the next pointer of the previous node and the back pointer of the next node. So first we locate the node we want to remove. So the previous node's next pointer is updated to skip the current node and point to the node after the current one. Similarly, the next node's back pointer is adjusted to point to the node before the one being removed. Finally, the node is deleted, freeing up the memory. We'll see step by step. Here, This one is, we are just locating the node we want to remove here. This one is pointing to the blue color node, so we located the node. Next we are pointing back and next, which is equal to pointing next, then pointing next and back, which is equal to pointing back, and then we'll delete PTR. We'll see here more images. First we are doing this pointing back and next equal to pointing next, which means this, we are just pointing back to next, which means pointing next. Then we'll do pointing next, pointing back, which means pointing back here like this. And then we'll do the delete PTR here like that. So this is how we can delete a node from a doubly linked list.